Have you ever stopped and really thought about a simple refrigerator magnet? I mean, it just sticks, right? It's sitting there defying gravity with this totally invisible grip. We see them every single day, but what we're really seeing is a tiny object tapping into one of the most basic, unseen forces in the entire universe. So yeah, let's dive into this simple, everyday magic.
And it all kind of starts with a question, inspired by this ancient tool, the compass. Seriously, how does this little needle know where north is? It's not just some clever piece of tech. It's like it's having a direct conversation with our planet. And the language it's speaking? Well, that's magnetism.
So, to figure out how a little compass can talk to an entire planet, we've got to start smaller. We need to get to the bottom of what gives a magnet its power in the first place. Okay, let's just tackle that head on. Is everything magnetic? I mean, can you stick a magnet to your water bottle or a wooden table? No, right? And there's a very good reason for that. Well, it turns out magnetism is kind of a special club, and only certain materials get an invitation. So things like iron and nickel and steel, they're magnetic. Why? Because deep down, on a microscopic level, their atoms are all lined up, all facing the same way, working together. But for most things in our world, plastic, wood, even some metals like brass, their atoms are just all jumbled up, a total mess. So they just don't feel that magnetic force at all.
Okay, so now we know what materials get to join the magnet club. But where does the real action happen? Where does a magnet's power actually live?
Is that magnetic force spread out evenly across the whole surface? Or is it all concentrated in one specific spot? Well, a really simple experiment gives us a beautiful, super clear answer.
And here's the secret. The power isn't spread out evenly at all. It's incredibly focused at two specific points. We call them the magnetic poles. And every single magnet, I don't care how big or small it is, has two of them, a north pole and a south pole. And this picture illustrates it perfectly. I mean, if you just dip a bar magnet into a pile of iron filings, you see this exact effect. The filings don't stick to the middle, they rush to the ends, creating these little fuzzy tufts. They are literally showing us where the poles are. It's so cool. And this leads to some pretty neat tricks. Let's say you have a magnet with no labels on it. How do you find its north and south poles? Well, you can actually use the Earth itself. Just hang the magnet from a string or float it on a piece of cork in some water and it will naturally swing around to point north-south. Or even easier, just grab another magnet that you do know and see which end pulls it in and which end pushes it away. All right, now we get to the really awesome part. We know about the poles, but how do two magnets talk to each other from a distance? How do they know whether they're supposed to pull together or push apart? The entire conversation between magnets comes down to one simple fundamental rule. You've probably heard this before, but it governs everything. Like poles repel and unlike poles attract. So a north will always push another north away, but it will always pull a south closer. That's it. It's the golden rule of magnetism. So this whole interaction happens inside something we call a magnetic field. Just think of it like an invisible bubble of influence that surrounds the magnet. It's basically a map of its power, and anything that wanders into this field is going to feel that force. And what's incredible is that we can actually see this invisible field. If you sprinkle iron filings around magnets, they trace the lines of force just like a map. Look at this. With opposite poles, see how the lines bridge the gap, physically showing that pulling force. But with two matching poles, the lines bend away, arching out to show that invisible push. It's just a stunning way to see a force that's normally completely invisible. So, we have all the pieces of the puzzle now. We know about magnetic materials, we know about poles, and we know about fields. So let's bring it all back together and solve our original mystery, the compass.
Because the secret isn't really in the compass itself. The secret is that the compass exists inside a much bigger magnetic field. That's right, our entire planet is basically one gigantic magnet. Now here's the part that's a little weird but also super cool. The north-seeking pole of your compass needle is attracted to its opposite, remember? Well, that means the spot up near the geographic North Pole is actually a magnetic South Pole. Your compass is just a tiny magnet, and its little North Pole is doing its best to line up with our planet's massive magnetic field.
And the beautiful thing about all this is you don't need any fancy tech to prove it. You can make one yourself, seriously. Just take a regular needle, stroke it with one end of a magnet to line up all its atoms, stick it on a piece of cork, and float it in a bowl of water. That is it. You just made a working compass.
So what you're seeing right here is that magnetized needle, which is now a tiny magnet in its own right, doing exactly what the Earth's enormous magnetic field is telling it to do: point north. It's that simple, it's elegant, and it just works. So we've gone from a simple magnet on a fridge all the way to an invisible force field that wraps around our entire planet. It really makes you wonder, doesn't it? I mean, if a simple magnetized needle can tap into a force that big, what other fundamental forces are out there, hiding in plain sight, just waiting for us to